Hey guys, welcome back to AlgoYogi. We are doing two-pointer series and our next problem in the list is kth symbol in grammar. Let's visit the problem on LeetCode. It says we build a table of n rows, one indexed. We start by writing 0 in first row. Now in every subsequent row, we look at the previous row and replace each occurrence of 0 with 0, 1 and each occurrence of 1 with 1, 0. So for example, when n is 3, first row is 0, second row is 0, 1, third row is 0, 1, 1, 0. So okay, let me just show you guys, but let me just finish reading it. Given two integers n and k, return the kth indexed symbol in the nth row. Alright, so what's really happening is we are trying to build a table, and our first symbol in when n is equals to 1, our first symbol is 0. So basically that's our base case, and since the problem is defined recursively, so we will basically try to solve it using recursion. All right, so when n is equals to 1, then this is my symbol. What will be my next symbol when n is, I'm going to change the color, when n is equals to 2, when n is equals to 3, when n is equals to 4. Okay, so what will we, let's generate our grammar. So this 0 becomes 0, 1, that was told to us. And what happens in n equals to 3, this particular 0 will become 0 and 1, right? And this 1 will become 1 and 0. It was told to us in the problem statement. And then we repeat the same step for our n equals to 4. So the 0 will be 0, 1, 1 will be 1, 0, 1 will be 1, 0, the 0 will be 0, 1. All right, what do we see? What do we actually see here? And just forget about returning k. So basically the k will be given in the combination of these n, and we will be basically returning kth indexed, and that too it starts at 1. So we will be returning one of these values. So if with combination n equals to 3, if k was given 2, then we would be returning this particular symbol. All right, so this would be the answer. This would be the answer, but we are trying to understand this pattern because this is not the only problem like this. So if we understand this, we will be able to solve a lot of recursive problems. Okay, although I would say this might be one of the easiest recursive problem. So what's really happening? See, can we see this pattern where our answer for basically next n, can we derive this pattern from using this when n minus 1? So this n equals to 3 is n minus 1 for my n equals to 4, right? So can I derive my n equals to 4 using this? So if you see, yes, we can. So this particular part, if you see over here, this is same as this part, right? This is same as this part. And how about the next part? How about this one? So basically what's happening is, let's see, and how is this number of these digits is affected when 0 and 1 binary digits is affected when this n increases by 1. So when n was 1, the number of digit was basically 1, number of digits. And I'm sorry, I forgot to tell you that this is basically the this particular part is basically the reverse of, if you basically flip the so basically if you flip these values, so 0 becomes 1, 1 becomes 0, 1 becomes 0. So it's basically not of these digits, right? So if you apply this not on every digit and you basically flip them and put them here, then this becomes my n answer, basically the nth grammar or whatever you guys want to call it. But I'm just trying to see this pattern. So number of digits would be when n is equals to 1, number of digit is 1. When n equals to 2, number of digit is 2. When n is equals to 3, when my number of digits are 4. When n is equals to 4, my number of digits are 8. What do you see here? we are doubling the digits at every step. So that would be n to the power, number of digit would be n to the power sorry, not n to the power, 2 to the power n minus 1, 2 to the power n minus 1. Okay, n minus 1 is because we are starting the index at 1, otherwise it would have been 2 to the power n, you know. So this time that's why my first one would be first one, actually you can see it here, you know. I should have just written this thing over here. So you can calculate using n to the 2 to the power n minus 1 for each of these. So what's really happening is, how about reaching to our answer now? So we have our base condition. This is a base condition. Our hypothesis would be, this induction step would be basically when I have, so if my k lies in this part, when my k lies, so k would be given alongside n. So in this case, let's say when n is given 4, my k would be, let's say my k is 2, then this is the answer that I'll be returning. This is the answer that I will be returning, this one. But I don't have this pattern generated right now, so I will be generating, or not really generating, reaching to the answer using my recursive steps. So what will happen is, I will try to find the mid of basically the length of my n equals to 4, I would say like the symbol, basically, you know. So when I'm trying to find the length here, that will happen, I'll find that out using 2 to the power n minus 1. That would be 2 to the power 4 minus 1, 3 to 2 to the power is 3 is 8. So it's 8 here. 8 by 2 will give me 4. 4 is basically 1, 2, 3, 4. 4 will be over here, this particular, and I'll check if my k is lesser than 4. Then I can simply call my basically answer onto the sub problem, this one, because this will be same as this k equals to 2 in my previous n minus 1. All right, so this is where I will reach. And how about I will try to call the same on my n equals to 3. So if I do that, when k is equals to 2, I will try to find the mid is right here, this one, and I'll check if my k is lesser than or greater than basically mid. Right now it's basically lesser than or equal to, so what I would do is, this part will be equals to n minus 1 again. Okay, otherwise what if k was greater? So this time it will be, you know, this time this will become, when n equals to 2 and k is equals to 2, then I will know that this becomes mid will become equal to k, right? So I will just return this this one from here. All right, otherwise what will happen is, or actually I'm so sorry, this is not what I meant. I meant this time when we will basically do n by 2 here, my half will be at 1, but my k is equals to 2. In that case, I will call not n minus 1. So basically if I have a function, let's say let me just write it, you know. So what I will have is, I'll have a function called solve, that solve for n equal n and k, and if n is 1 and k is 1, then I return 0. That is my base case. And if, which is like, let's find out the mid. So mid will come from 2 to the power n minus 1 divided by 2, right? So this mid, if k is less than or equal to mid, then I will return solve n minus 1 and k, because this will lie in the first half, right? Otherwise, what I'll do is else. I'll say just else, because right now this won't happen. So else case would be basically k will be greater than the middle of the generated string. Else solve n minus 1 but k minus mid. Why k minus mid? Because first half is not of use to me anymore, but I know in the next remaining values this has to be calculated. Basically again I will have to use k, but I have to basically get rid of the first section, first half, and then again this k will start, like this k will start again, because that length is what we are feeding into. I'm trying to reach that offset, if you get it. And I think that, but in this case remember, we will flip the values. And in Python there is a thing, if you basically subtract this by 1 instead of doing this, that will flip all the values. And I think you can look this up. This works for me. I've tried it, and I think because we're dealing with these two digits, binary digits, and this explains why that would happen. All right, I think that is it. Let's code our solution. It will be pretty easy. We already have the pseudocode here. Okay, I'm gonna switch the view. All right, so let me actually put it on charging. Yeah, I'm not shooting these videos like really professionally, but I'm just solving these problems myself and just recording it. You guys should also do it. I guess that's one of the best ways to prepare. Okay, so now it looks good. So let's write our solution. So what's really happening is we're gonna let's define a this inner function. Let's call it solve. Feed in n and k. Base condition: if n is equals to 1 and k is equals to 1. Yeah, I forgot. In Python that doesn't work. So k equals to 1, and then we return 0 because that was our first digit. If, let's find out the mid first. So mid would be 2 to the power n minus 1 divided by 2. That will give us the mid. And if my k is less than or equals to mid, then I want to call solve because at the end of the day what we're returning is coming from either 0 or 1, so it would be solve n minus 1, and k will remain intact because it will be, k will count from the beginning, and this will come from right from the beginning at index 1 basically. So k can count from the beginning. Otherwise else we need to return not solve. N minus 1 is good, and this will be k minus mid. If k is greater than mid, then k needs to be calculated in the second one, that too flipped. So this note will flip it. We understood why, in the conceptual part, why we need to flip it. And I think that would be it. But remember, in Python actually we do it by subtracting it from 1. That's good now, I think. Now let's just return solve on our end and k. Okay, I'm gonna zoom out and let's try to run it on the example. All right, and I'm gonna submit it. Awesome. So okay, so what will be the time complexity here? Time complexity is going to be it's a really efficient solution. Time complexity would be log n, wouldn't that? Because you are basically solving, like, you have these n, and you are basically breaking it into half basically each time, so that's pretty understandable. It will be log n. Okay, and space complexity, actually inbuilt, outside we are not doing it, but since it's a recursive function, inbuilt space complexity would also be log n. All right, okay, it's done. Let's go back to our AlgoYogi, mark this problem solved, and see you guys in the next problem. Until then, bye bye.